Okay guys, I'm going to take a pause here and we're going to go back from the very first day when I came to class, and we are going to I'm going to try to wrap this all up in a package before we do multi-compartmental modeling. Multi-compartmental modeling, sometimes I do that earlier, I'm doing it later this time, but it kind of doesn't necessarily fit easily with all this the actually physiological determinants of all of these things. So I'm going to try to put this all together for you. And this is going to be a long video. I apologize already because I don't want to stop since it's sort of the summary. If you'll remember back in the beginning, basically I told you we're trying to figure out what's the best dosage regimen design that we can come up with for our patients to make sure that they are both safe and effective with the doses that we're giving our patients on an individual basis. So to do this, we need to figure out our dose rate and our dose interval, right? So, sorry, I didn't mean to do that. So we need our dose rate and our dose interval. We know to determine our dose rate, we want to look at our CSS average and see if it's where we want it to be, right? So in order to determine our CSS average, the determinants of CSS average are bioavailable dose rate, drug in over drug out, clearance. If there is a salt form involved, then we have to also consider that. So I've just put the definitions here for you, but I'm sure you already know those. Dose interval is determined by your peak to trough ratio, right? So your peak to trough ratio is determined by 1 over e to the negative k tau. We choose tau, right? Dose interval. So what really determines our peak to trough ratio is what we determine, the tau, and that slope of our elimination curve, which is determined by clearance and volume. We can also look at it by looking at the half-life. And as you probably remember, we're going to dose about every half-life. So sometimes looking at half-life just saves a little bit of time. But what determines all of these? Well, the things that it comes down to, right, is, oopsie, didn't mean to go backward. Bioavailability, which is a determinant of CSS average. Clearance, which is also a determinant of CSS average. Volume, which is a determinant of K and half-life. And then clearance again. So remember, now we're going to dig deeper on those three important parameters: bioavailability, volume of distribution, and clearance. So we're going to start out with bioavailability just like we did in class. So we're going to go over what determines bioavailability. We're going to dig a little deeper. What are the determinants? What determines bioavailability? Well, you know this now. It's FA, fraction absorbed, which really just follows the rules of passive diffusion. So you just need to know the rules of passive diffusion and you will understand fraction absorbed. It's a fairly simple concept. It is not Michaelis-Menten because you can't overwhelm it. It's just a passive diffusion, so it's all about that concentration gradient and the drug being in a form to pass through that membrane. We have the fraction that gets absorbed. We have the fraction that makes it through the gut metabolism. When we say gut metabolism, we know that there's enzymes waiting in that gut to metabolize our drug. Usually the CYP drug, specifically CYP3A4, is in a lot of there's a lot of CYP3A4 in the gut, and the P-glycoprotein. P-glycoprotein, you know, is the bouncer of the body. So these enzymes and P-glycoprotein can be inhibited and enhanced, right? So we can have them blocked or we can have them increased. So that is a site of drug interaction. So is the fraction absorbed, right? Then we also have the fraction that escapes hepatic metabolism, which you now know is equal to 1 minus E, E being the extraction ratio for hepatic clearance. So how much drug makes it through that liver. For low extraction drugs, or for drugs that are cleared renally, almost all of the drug is going to make it through the liver, is going to escape that metabolism, so about 100%. So FH will be reaching 1 for drugs that are cleared renally or drugs that are low extraction cleared by the liver. For drugs that are cleared by the liver and are high extraction, we're going to have more of the drug removed, and this is going to be the determinant with this fraction unbound equaling 1 because of non-restrictive clearance. Because these things are involved is why we have route dependence or route dependence, right? So the determinants of bioavailability are there, FA, FG, and FH, and you should be able to determine all the drug interactions that could occur because of that. So that's what determines bioavailability, but what does bioavailability determine? Well, it determines, as we know, CSS average. Determines CSS average. Bioavailability determines CSS average. We can just plug this in for our F there, can't we? And if we know what the FH is, we can plug that in. There will be things that still can affect FA and FG though, right? So it determines CSS average and CSS free. If we want free, we just multiply this whole thing times fraction unbound, right? So therefore, bioavailability may result in dose rate changes. Now we're going to talk about volume of distribution. What determines your volume of distribution? Well, the determinant of volume distribution is this equation here. So we know we have volume of plasma, which is 0.4 liters per kilogram in a person. And then we also have our volume of tissue, which is 0.54 liters per kilogram in a person. And then we have this all-important relationship between the fraction unbound in plasma and fraction unbound in tissue. And we know that it really comes down to this relationship here, and it's really all about these changes in plasma and tissue binding that will result in changes in the volume of distribution. So what does the volume of distribution determine then? Well, we know it helps determine what our loading dose is going to be, right? Our VC, that initial volume. We also know it's a determinant here in both K and half-life. Therefore, it's going to help dictate our dose interval. Now, when we think about really what's changing volume, it's plasma and tissue protein binding. So what are the determinants of protein binding? So we're going to dig one level deeper so that we can understand what determines binding. We know that there's a limited number of binding sites, so there's a limited number of protein binding sites. So this follows Michaelis-Menten kinetics. As you can see, this equation is the Michaelis-Menten form, right? The concentration bound will be equal to the N total, which is the number of binding sites available. So it's the capacity of the system. It's analogous to Vmax, right? That times concentration all over Kd plus concentration. Kd is the concentration where half of the binding sites are occupied. This is analogous to Km, so it's the affinity constant. So this is what determines binding. That's important to understand because what does protein binding determine? It determines a lot of things. It's quite important, isn't it? It's the most important thing to determine volume of distribution. Both plasma proteins and tissue protein binding are going to determine your VSS. It is one of the determinants of clearance for low extraction drugs, because for low extraction drugs, the clearance is approximated by intrinsic clearance and fraction unbound in plasma. It's also a major determinant in your filtration clearance. When your fraction unbound in plasma changes, you cannot, this is very important, right? You cannot trust your C total. The only time you have to look at CSS free is when there's been a binding change in the plasma. When there's been a binding change, you must look at C free, not at C total, because you can't to decide what you're going to do. Because we know CSS free is just CSS total times the fraction unbound in plasma. This is a really important point, guys. So binding, you can see, is very important, so we need to understand it. Okay, so we've talked about bioavailability, we've talked about volume distribution, and now we're going to talk about clearance. What determines clearance? Well, this is a very involved slide, but it kind of sums up what we've been doing for the last several weeks. So, clearance is determined by blood flow to the organ and the extraction efficiency of that organ. But in order to get down to what we really want to know as far as what determines clearance, the first thing we need to know is how is it cleared. So we ask, what is the FE? What's the fraction excreted unchanged in the urine? If the fraction excreted unchanged in the urine is 0, then it's hepatic, right? And if it's 1, then it's renal, isn't it? Let's go with hepatic first. So if we know that it's hepatically cleared, then we say, what's its extraction efficiency? Is it a high extraction efficiency or is it a low extraction efficiency? So if the E is approaching 0, then it's a low E. And we know that clearance is going to be dependent upon enzyme activity and binding, don't we? And we know that the fraction that escapes that first pass effect is approximated by 1. We also know that it's going to undergo restrictive clearance, which means that only the free drug will be free for being eliminated. Only free drug will be fair game for those enzymes. So E will be limited by just the drug that is unbound. If it's not a low E, but a high E, I'm going to change my color here. So what if it's high E? Then we know clearance is dependent upon that blood flow, isn't it? And now we've got the tricky fraction that escapes first pass effect. This is why we have route dependence, right? We only see route dependence with high E drugs because of this relationship. And now we can't see this, but E is greater than your fraction unbound because this is a non-restrictively cleared drug, which makes this fraction unbound all seem as 1 to the liver. So that's what's going to determine clearance for a high E drug cleared by the liver is Q, and for a low E drug it's going to be intrinsic clearance times binding, but I gave you a bunch of other stuff that you need to know as well. Okay, what about if the drug has an FE of 1 where it's a renally cleared drug? Well, then the next thing we want to ask ourselves is, what's the predominant process? Remember, we have filtration, secretion, and reabsorption. We know all drugs are going to be filtered, but which is predominant, secretion or reabsorption? Well, if the drug's filtration clearance is less than what is actually cleared by the kidneys, we know drug is being added to the tubule, which means the predominant process is secretion. So remember, this is another Michaelis-Menten situation where you have to have transporters to take the drug into the urine. So we're going to be looking for, for drug interactions, we're going to be looking for other like drugs, like acids competing with acids, or bases competing with bases. But they'd have to be secreted drugs with a lower KTS to displace our drug from its protein binding site. So for secretion, that's what we're looking for, our competing drugs. What about if the predominant process is reabsorption, and we know that because the filtration clearance is greater than what goes out into the bladder and out of the body. So the drug must be being reabsorbed back into the body. Here this is a passive process, right? So the secretion is active, but reabsorption is just passive diffusion. So we're going to look for changes in urine pH, which will change the ionic character of the drug, either enhancing or blocking reabsorption. And we're going to also look for that concentration gradient to be maintained in order to drive the reabsorption. If the concentration gradient is ruined, you're going to have a decrease in reabsorption. And if you reestablish that by getting rid of a diuretic, then it will enhance reabsorption. So that's a summary of what we've been doing the last couple of weeks, right? So what does clearance determine? We know clearance is really important because not only does it, is it a determinant of CSS average and CSS free, it's also a determinant of half-life and K. So CSS average and CSS free is going to mean that it will determine if there's a dose rate change, and half-life and K will determine if there's a dose interval change. So we can see clearances here determining CSS average, and clearances here determining our dose interval. Now, we need to dig a little bit deeper here and talk about what are the determinants of intrinsic clearance. Intrinsic clearance follows Michaelis-Menten, because intrinsic clearance, hepatic intrinsic clearance is enzyme activity. It's the number of enzymes available and the relationship between the drug and the enzyme itself. Because there's a limited number of enzymes, it also follows Michaelis-Menten, which you can see here. Vmax are the number of enzymes available, so it's the maximum rate at which you can clear the drug. So this defines the capacity of the system. Km here is the concentration where half of the Vmax or half of the enzymes are occupied. This is all about affinity, isn't it? So we'll either have an increase in the number of enzymes or a decrease in the number of enzymes, or an increase or decrease in the relationship of the affinities of two drugs that will change our intrinsic clearance. Why is intrinsic clearance important? What does it determine? Well, intrinsic clearance, hepatic clearancy, I guess I can't spell. I have to fix that slide. Intrinsic hepatic clearance determines the clearance for low extraction drugs, the hepatic clearance for low extraction drugs, because it is one of the main determinants of clearance for a low extraction drug. High extraction drugs it's not a determinant of, but it's also, for high extraction drugs, it's a determinant of FH, isn't it? So it's going to determine bioavailability for a high extraction drug, but for a low extraction drug, it's going to determine clearance. So that's interesting, isn't it? Now, pharmacodynamics, which we're just learning about now. So why do we need to know pharmacodynamics? Well, it sort of pulls everything together, doesn't it? I don't know why I need to write on that. What determines the effect at a given concentration? So what determines pharmacodynamics? The things that determine pharmacodynamics are is this model of our effect being determined by the Emax times concentration all over C50 plus concentration. This should start to look very familiar. Again, it's Michaelis-Menten, isn't it? Because we have a fixed number of receptors, so our Emax is our maximum effect. Probably, if you want to think of a receptor situation, it's the number of receptors available for an effect to occur. Concentration is our concentration of our drug, so it's all about this relationship between concentration and effect. Concentration determines effect, right? So we have Emax and C50, just like we would in any Michaelis-Menten situation. C50 is the concentration where half Emax occurs. And again, you can think about half of the receptors that are needed to cause an effect being full. And it's analogous to Km. So this is the affinity and the capacity of the system and concentration. This gamma slope factor is really a mechanism to make the model fit, and does tell us something about that relationship between concentration and effect, doesn't it? About the slope, right? So this gamma Why do we care about pharmacodynamics? What do they determine? Well, in the end, they determine the target concentrations that we need for our given effects. Well, that didn't take that long. I was worried it might take long, but I moved pretty quickly, hopefully not too quickly, and you can go back and review. I hope this kind of ties everything together for you, and you understand why we've been studying all these things, and it may help you, I hope, in studying for the final as well. Thank you for your attention.